So in the previous section, we looked at the integral when the region of integration is a rectangular region. So you have double integral over r of f of x y dA, and r is maybe a region from A to B, and then from C to D, A to B on the x-axis, and C to D on the y-axis. Now, if you look at this region, you can think of this as a line, this as a line, and think of this as y is a constant function, y equal to c, and this y is another constant function, d. And then so you're looking at this, the region bounded by these two functions, okay? Y equals d and y equals c. These two functions, think of this line as the graph of a function and this as the graph of another function. And then you're just going from A to B. You're looking at a region bounded by the two functions from x equals A to x equals B. That's one way to look at it. And when we did this, we said, oh, this is the integral from C to D, right, of f of x, y, dy, and then A to B dx. Now, a general region would be if instead of having the function be a straight line, you now have on the y-axis, you now have maybe a function like this. So instead of y equals c, it's no longer a constant function. It's say y equals maybe g of x. And then you now have maybe another function like this, y equals, say, f of x. Or let's do this. Let's make this h of x for high and then L of x for low. But then on the x-axis, we're still going from A to B. So we're looking at a region that's no longer a rectangle, okay? A general region. So this is your R here, okay? So in this case, for a general region, our integral, the integral over R of f of xy dA is now going to be the integral, the inner integral from L of x to h of x of f of xy dy, and then from A to B f of xy dx. So that's what we're going to be looking at, okay? That's what we're going to be using from now onwards. And some different iterations, different manipulations of it. Let's look at one example. Let's look at an example one. Number one. So we would like to evaluate the integral r x plus 2y dA, where R is the region bounded by the parabolas y equals 2x squared and y equals 1 plus x squared. Okay. So I haven't warned you about this, but I'm going to warn you now. Whenever you're given this kind of problem in the general region, if you want to solve the problem, you really need to sketch the region of integration. It's very important. So let's start by sketching the region of integration. We have y equals 2x. So we have something like this. All right. Y equals 2x. No. I didn't say, I said 2x. 2x squared. 2x squared. And then we have y equals 1 plus x squared. Something like that. So this is y equals 1 plus x squared. So there are 2 points of intersection, and this is our region, the region we're going to be thinking of, okay? So this is their points of intersection. What are their points of intersection? Okay, in order to use this region, we have to find these points of intersection. So first, we find points of intersection. What are points of intersection? You set 2x squared equal to 1 plus x squared. When you solve this, this becomes x squared minus 1 equals 0. So that tells us that x is equal to plus or minus 1. So this is minus 1. This is 1. Now we are ready to set up our integral. So with this, the integral r over r of x plus 2y. I had dx here, but I said dA. That's what I meant, dA for area. dA is going to be, the inside integral is going to be the integral from 1 plus x squared, y equals 1 plus x squared, because 1 plus x squared is the lower function. It's the lower function, right? The lower function to 2x squared, the higher function, the one above, of x plus 2y, and then we're going to go dy, and then we're going to go from x from negative 1 to 1 on the x-axis, dx. So what you have to do is you have to take the integral, do the integration with respect to y with these limits, and then after that, do the integration with respect to x. I want to point a few things out before we perform this integration. The first thing I would like to point out is that you can see now in the general region, the bounds of integration are usually constants, but here you can see the bounds of integration is not a constant. In the inner function, is not a constant. However, the outer function, the bound of integration, has to be a constant. That's the first thing I wanted to point out for general regions. The bounds of integration for the inner integral is usually not a constant. Another thing I would like to point out is that in this case now, Fubini's theorem doesn't apply. You can't switch the integrals easily. You can't just switch them anyhow. Okay? We will discuss switching integrals for general regions later on. Okay, so let's perform the inside integral. If you do the inside integral, you're taking the integral with respect to y. So this is just going to be xy plus y squared, okay? And then you're going from 1 plus x squared to 2x squared, okay? You're plugging in 1 plus x squared, plugging in 2x. But you're still taking the integral of this whole thing, dx. So let's now plug in 1 plus 2x, and let's plug in 1 plus x squared, and let's plug in 2x squared. So we're going from negative 1 to 1. if we plug in 1 plus x squared for y, we get x times 1 plus x. No. Let's plug in 2x first. 2x squared. All right. 2x squared plus 2x squared squared. Okay. And then we're going to subtract. You now plug in 1 minus x squared. So x times 1 minus x squared plus 1 minus x squared squared. Actually, 1 plus x squared. Where did I get 1 minus x squared squared? So this is kind of some giant polynomial, degree 2 polynomial, and then you still have your dx. Okay. I am glad to tell you that if you simplify everything inside, you're going to get negative 3x to the fourth. Actually, not degree 2, degree 4. 2x to the fourth minus x cubed plus 2x squared plus x plus 1. I did it beforehand. So, and I want you to check my answer. And you still have your dx. So all I'm saying is that if you simplify what's inside here, you're going to get this. Okay. So this now becomes a little easier. You have your dx. Find the integral with respect to x. The antiderivative, you have negative 3x to the fourth, x to the fifth now over 5, minus x to the fourth over 4, plus 2x cubed over 3, plus x squared over 2, plus x. And then you're going to plug in negative 1, plug in 1. When you do that, you end up with negative 3 over 5 minus 1 over 4 plus 2 over 3 plus 1 over 2 plus 1, then minus 3 over 5 minus 1 over 4 minus 2 over 3 plus 1 half minus 1. I think I got everything. And if you play with these numbers, use your calculator or just do it by hand. Actually, a lot of things can be done by hand. Things will cancel out because you have the ones that are the same will cancel out because you're subtracting. You have negative 1/4. You're also subtracting negative 1/4. You have 1 half and you're also subtracting 1 half. I think those two will cancel out. That makes it easy. But when I did it, I got 32 over 15. That's what I got. Okay. Now let's try another problem. Not a problem. All right. Let's evaluate XYDA, where R is the region. R is the region bounded by y equals x minus 1 and the parabola y squared is equal to 2x plus 6. Okay. So I'll begin by looking at the region of integration. First of all, we have this parabola that is usually parabolas, you have y equals 2x squared or something like that, or y equals some constant times x squared plus another constant. But this one, the squared is on the y. So let's solve for x. So this is a parabola where you have x is equal to a function of y. You can rewrite it that way. So if we go that route, we end up with, if you rearrange this, solve for x, you get x is equal to 1/2 y squared minus 3. That's what we get. So let's bear that in mind. We have two functions, one function and another function. So since we've written the second function in terms of y, we can also write this in terms of y. We can write it as x is equal to y plus 1 if we need to. So let's begin by sketching our region of integration. Our region of integration, we have our y-axis, and then let me make it a little darker and a little bolder. So, okay. So, on that x-axis. Now, think of this is x, all right? And this is y, okay? So x is a function of y. So what do we do if we take this, I'm going to do something, I'm going to copy this, I'm going to paste it here, I'm going to rotate this. Oh no, I can't. Oh, yep, I can do it. I can do it. Okay. So think of this now. And instead of making this the positive x-axis, I'm going to flip it around and make, oh no, I didn't ask you to do that, okay? All right. So I'm going to make this the positive y-axis. So if you want to sketch the graph, x is equal to 1/2 y squared minus 3. Now, you can sketch it. You can actually if you think of the y as the positive x-axis, if you think of the vertical axis as the positive, as the y-axis, and the horizontal axis. No, what am I saying? Think of the vertical axis as the x-axis and the horizontal axis as the y-axis. That's what I'm saying. It lends itself to this function, to this particular function. So how about we do that? If we sketch this function, it's just going to be a graph where you have a parabola whose vertex is at -3. The x-axis, something like that, like this. Okay? Okay, so the whole point of doing this is to let you know that this particular parabola would have its vertex on the x-axis, the negative x-axis. So we have something like that. Okay. All right, for now, I'm going to erase this. All right, so now we can now draw this is the function x equals 1/2 y squared minus 3. And then we can draw the next function, which is x is equal to y plus 1. Okay. So the whole point of switching everything to make x a function of y is because of the region we're given, because of how the parabola is structured. So this is our region. Let's make it very light blue. So this is the region we're dealing with. Okay. And just like before, we need to find the points of intersection, this point and that point. How do we find the point of intersection? We set them equal to each other if we set y plus 1 equal to 1/2 y squared minus 3. If we multiply through by 2, we might end up with 2y plus 2 is equal to y squared minus 6. You can do this however you want. So you get y squared minus 2y minus 8 is equal to 0. When you solve this, I believe you get, I'm going to guess the answer. Well, let me not guess. I believe you get negative 2 and 4. So if you plug in negative 2 in the first one, you get 4 plus 4. Yeah, negative 2 and 4. Negative 2 and 4. That's what I think you'll get. Okay, so that means on the y-axis, this is negative 2 and this is 4. Okay. Now, just like before, we can now write an expression for our region, integral dA. We're going to the inside. Now, things are going to change a little bit. Not a little bit, just a little bit of reversal. Not too much, but it makes sense. So we're going to go from, we have our x, y, but since the functions are now functions of y, x is a function of y, we begin with dx, and our bounds are now a function of y. We're going the top. We're going from left to right. Left is now the lower function. The left function is now the lower function. This is the lower function. And the right one is the higher function. Okay. Lower, higher, or low and high, or top and bottom, or bottom and top. But what I'm saying is that the top function is going to be 1/2 y squared minus 3, and the bottom function is going to be y plus 1. Okay, so that's the x. Whenever you have the x here inside, then this function has to be a function of y, And then we try the next integral. It's just going to be from negative 2 to 4 dy now. So you perform this integration first, and then you perform this one later on. Okay. I don't know how much of this I can do, but I would actually want you to try it. So if you do the x first, you have x squared y over 2, and then you're plugging in y plus 1 and 1/2 y squared minus 3. And then you're still remembering negative 42 dy. Okay. And then in that case, negative 2 to 4. You can factor out a 1/2, but you're now plugging in y. For x, you're plugging in 1/2 y squared minus 3 squared times y minus you're now plugging in y plus 1 squared times y. So it's not going to be a trivial algebra, but you see what I'm doing? You just keep simplifying that. I think the answer I got is 36. I want you to try it and tell me that my answer is right, okay? Okay, so that is 2 problems that we've done so far. Okay, now let's try another problem. let's find the volume of the tetrahedron, right? And tetrahedron is just a pyramid with four rectangular faces. Actually, triangular faces in this case. In the first octant, and I'll explain what that means. The first octant, bounded, not beyonded, bounded by the plane z equals 2 minus x minus y, and the coordinate planes x equals 0, y equals 0, and z equals 0. All right. Okay. So we have a plane. This is the plane that we're dealing with. We need to sketch the plane first, okay? Or to try to sketch the plane. This is the plane we're dealing with. We're trying to find the volume of this plane. So we have z-axis, x-axis. Let's do this. Let's make it a little darker. That's all I want. That. Oh no. Make it dark. All right, that's good enough. Okay. So this is the x-axis. X or y. This is x. And this is z. Okay. Now, the coordinate planes are this plane. This plane x is 0. This is another coordinate plane. Y is 0. And this is another coordinate plane. Z is 0. Okay? So, we would like to find the intersection of the plane, our plane, with the axis. We know that the plane, that our solid, our tetrahedron, is formed using these planes, the coordinate planes, and the plane we're going to draw. So the plane we're going to draw is probably gonna be something like, it's gonna intersect it this way, so that it has this face, that face, this face, right? And then its face, which is determined by the plane. All right. So that's what we're going to do. We're going to find the points of intersections, these points, and go from there. All right. So to find the points of intersection of the plane with the axis, you just have to set the axis equal to 0. So for the x is equal to 0 plane, its intersection with the plane, or the axis intersection with, let's call it the y-intercept. Why not? Y or x-intercept. That was what I meant. X-intercept. At the x-intercept, every other thing is 0. Z is 0, y is 0. And in that case, we just get x is equal to 2. Y-intercept, x is 0, z is 0. So y is 2. So this turns out to be actually very easy. And then z-intercept, x is 0, y 0. So we get z equals 0. All right, so our intercepts are at 2, all of them. Okay, so our plane looks like this, then that, and then that. Okay, so that's the plane. So these are the 4 sides of the tetrahedron. The sides formed by the plane, or let's start with this, that point, that, right? And then the floor. I'm going to call the floor R. I know I'm calling it R. Okay? So those are the three faces, and then the 4th face is the plane itself. Okay? But what are we trying to do? We're trying to find the volume of this tetrahedron. So we are going to be solving an integration problem. To solve an integration problem, we now have to figure out our region of integration. And our region of integration is sitting there, is the R on the floor of the XY plane. So we just want this region, R. I drew it in green, so let me make it green here. This R region, right? So this is our x-axis, this is our y-axis. Okay. The intercept, the y-intercept is 2. Another x-intercept is 2. So what's the slope? You can find the slope, right? The slope is negative 1, right? That's quite easy to find. So this function is actually y equals 2 minus x. You can check it. All right. I'm going to put it by the side over here. So we have our region of integration. Then our volume now, which we're computing, we're trying to compute the volume V. The volume of this solid is V, is the integral over the region R of 2 minus x minus y. Because that's our function. This is our function here. Z is a function of xy, and it's 2 minus x minus y. All right. So we can do dy, dx. We could also do dx first, but not really this time. Unless we rewrite our function, x is a function of y. Here, we can rewrite it as x is equal to 2 minus y. But let's just do dy first. So that means we're going from y, this y is equal to, let's do this. This is when y is 0. Y equal to 0 to y equals 2 minus x. Okay? This line to that line. And then we're going x from x equals 0 to x equals 2. So let's start y equals 0 to 2 minus x. So you have 2 minus x minus y dy. And then we're going x from 0 to 2 dx. Okay? So again, you take the antiderivative with respect to y first, which will give you 2y minus xy minus y squared over 2. And then you plug in 0 and 2 minus x. And then you go from 0 to 2 dx. Okay? So I'll let you finish this. The answer I got is 8/6. I want you to verify it yourself. All right. I want you guys to try 2 problems. The first problem is this. To evaluate 0 to 1, x to 1, of sine of y squared dy dx. Okay. This is going to give you some tough time, but I want to discuss the problems you encountered and how to solve it. All right. The next one is I want you to find the volume of the solid region bounded by the paraboloids y, z equals x squared plus y squared, and z equals 8 minus x squared minus y squared. Okay. I just want you to set it up. How about you just set it up, not solve the whole thing. I want you to set up the integral. So the paraboloid, one of them is this, something like this, and another is that. Oh no. Like that. So this would be z equals x squared plus y squared, and this would be z equals 8 minus x squared minus y squared. Okay. So we're looking for the volume. All right. So all I want you to do is set it up. Okay. Let's see how you do it. Okay. Try. I usually write try this, so let's maintain that tradition. Try this. Okay, this is a lot, but it's good. I will see you on the next video and in class.